If you've watched the video for the blanket toss, what you're going to see is that they're doing something sort of like a trampoline. The difference here, though, is that the people are actually very actively part of it, so that instead of just hitting like a trampoline and you're depending on springs to kind of make you bounce back, the people on the edges can actually do things like pull on it to make it more tense, or to kind of pull back on it and fling you back up and things. So they are very active in this event. In the video, you can see this person being thrown up really high. Apparently there's some blanket tosses where they'll actually throw people like up to 9 meters up in the air. It kind of sounds dangerous to me, but I guess, especially if you have people that are really good at judging the feel in the blanket, it could be done relatively safely, I guess. Now, in this particular example, we're saying that a 75 kilogram person is thrown 2.5 meters up into the air. Now, that's relative to the blanket, not to the ground that's somewhere below. We're using the blanket as our reference point. And I say that when the person comes back down and hits the blanket, the collision event, they slow the person down over a period of 1.15 seconds. So that's our collision event. That's not the time up into the air or falling back down. That's the actual collision event that's happening. So in the first question, it says that I want to determine the velocity of the person as he initially strikes the blanket. So that means he's falling, okay? He started at that maximum height that he was at, and he's had all that time to fall and speed up faster, faster, faster. So as he strikes the blanket, he's going the fastest he ever will. One way that we could approach this is Vf squared equals Vi squared plus 2AD. At the very top height, he's not moving. Oh, and I should say that we're going to be square rooting all of this. He is falling because of the acceleration due to gravity, and he fell from an initial top height of 2.5 meters relative to the blanket. Please make sure that when you put that in, you put in a negative sign on it because they fell 2.5 meters. When we take our square root, two negatives are a positive, so we're okay for taking the square root. We come up with a final velocity that works out as 7.0 meters per second. Now the importance there is, because we were doing a square root, we can't see the positives and negatives. This is basically an absolute value, but he came down at 7.0 meters per second. So we should take that into account when we write it into our answer. We could also do this in terms of energy, because all potential at the top, all kinetic at the bottom, cancel out the m's. We get a formula that says square root 2gh, where this really is this. 2 times gravity times height, square root of the whole thing. So it gives us the exact same answer. Again, we have to take into account it's an absolute value, so we put on the negative sign to indicate the direction. Now it says here, explain the importance of relaxing the blanket as the person strikes, rather than holding it tightly, okay? So here's what we gotta consider. For that person to stop because they hit the blanket at 7 meters per second, in this part, we're basically saying, for whatever their mass was, 75 kilograms, I think? Yes, 75 kilograms. The final velocity has to be 0, and we're subtracting negative 7.0. That's the impulse that has to be caused. Now, whatever else happens, that's the impulse that has to happen to stop the person. If we look at the other part of the formula, F delta T, and we solve it for force, that's where we're saying it's the force that's actually going to potentially injure the person. So this impulse, whether they hold it tight or not, is actually going to stay a constant. This part up here stays a constant, just like in an airbag question. Down here is where we can change things. By relaxing the blanket as the person hits, they magnify this time. They make it bigger. The collision event takes longer. If this number on the bottom gets bigger, the force will get comparatively smaller. So the more they relax it as the person hits, the smaller the force will be. If they held it really tight, the time of the collision would be very short, and that would maximize the force, actually mess the person up. So in this question down here, where I say determine the force that's being exerted on the person in order to stop them, I'm actually asking you to do all of this stuff. Now, unfortunately, I do not have written down what that part was equal to, but whatever it is, when you put that impulse in over here with the 1.15 seconds, you should get a force that comes out as 457 newtons. Now, that force is acting upwards because it has to stop the person who was coming down. Negative velocity, negative accelerations, a positive force pushing up is going to be what stops the person. So 457 newtons, that's actually still a pretty good lick of force. We're not talking about breaking bones necessarily, but you're definitely going to feel that. Now, at the very bottom of this, I say, hey, draw a graph that shows something about realistically what would happen if the person was hitting and that the force isn't necessarily uniform. Because you know what? As the person hits, maybe they're holding it tighter initially and then they kind of relax it to absorb the person, or maybe they were holding kind of loose and then as he hits they pull harder and then relax it. There's actually different versions of what this could look like. Maybe you draw, and this is for this question, maybe you draw it so that it looks like this. They were holding it really tight, and as the person hit, they decreased their force. They let it go a little bit loose to expand that time interval. Maybe somebody else says that when they were grabbing the blanket, initially they're holding it kind of loose, and then as the person hits, they realize, oh, we have to pull harder so that they don't just hit the ground or something, and then they relax it. These are actually, I think, two legitimately correct answers, depending on exactly how you're explaining what's happening during that collision. They could both be realistic interpretations of what's happening. And then, if you had graphs like this with actual genuine numbers, what you could do is calculate the area under one of these lines, and that would actually be the impulse that was acting on it. So it could actually be a different sort of question then because of that.